Hello, my name is Justin Koehler, and I am with Risk Management Professionals. Today, I will be covering the topic of off-site consequence analysis, otherwise known as hazard assessments. The key topics I'll be discussing today are the general off-site consequence analysis guidelines, regulatory guidelines, modeling, and physical properties. The definition of off-site consequence analysis is as follows. In broad terms, the distance to the endpoint is the distance a toxic vapor cloud, heat from an explosion, or blast waves from an explosion will travel before dissipating to the point that serious injuries from short-term exposures are no longer likely. Off-site consequence analysis, otherwise known as hazard assessments, are required by the California Accidental Release Prevention or CALARP program and Risk Management Prevention RMP programs. Program level is dependent upon regulated substance, quantity, and off-site impact. The typical hazardous substance that we model are flammable and toxic substances. The two types of modeling that are done on hazard assessments are worst-case release scenarios, which dictate the furthest endpoint from a possible release, and are modeled off of the largest storage vessel, and alternative release scenarios, which are the more likely than worst-case scenarios to occur. The covered process should include what the regulated substances are, how much of the regulated substance are on site, what kind of process that the chemicals are involved in, and where the chemical is located on site. Toxic endpoint. Usually measured in parts per million, or ppm, the Emergency Response Program guidelines give an ERPG 1 and 2 value, which are usually the non-lethal exposure after 1 hour, and the immediate danger to life and health, or IDLH. This value could cause immediate threat to life or irreversible damage or inability to escape from a dangerous atmosphere. And also reported is the median lethal dose, or LC50, the point at which 50% of population of animals would die from exposure within a certain amount of time. For flammables, an explosion case is seen with an overpressure of 1 psi and a radiant heat exposure of 5 kilowatts per meter squared for 40 seconds. When modeling for the worst case scenario, the atmospheric stability class is as follows. The wind speed taken into account is 1.5 meters per second and an F atmospheric stability class. This minimizes convection and assumes that the vapor cloud or flammable vapor cloud is at 100% of its saturated capability. For alternative case, the typical wind speed that is measured is 3 meters per second and a D atmospheric stability class. This assumes that there's a slight breeze going and mixing up the vapor cloud so that the distance isn't as far. This is your typical day. The surface roughness that is accounted for are as follows. Urban and rural. Where urban, there are many obstacles in the immediate area, including buildings, trees, etc. And rural, there is no immediate obstacles in the area, and the ground is flat with no obstructions. The types of releases that we have are typically gas, liquid, and solid. The passive mitigations that are accounted for in each case are dikes, enclosures, berms, drains, and sumps. These are considered passive mitigations because they don't have to be activated in the case of an emergency. For accidental releases, your 5-year history is reported during the hazard assessment. These instances cover on-site deaths, injuries, and significant property damage, and off-site injuries, sheltering in place, property damage, and environmental damage. These instances should be reported immediately and kept on site for the remaining process time. But only the 5-year history needs to be reported for the hazard assessment. Sensitive receptors are the population estimate within the circle of concern. These include child daycare facilities, long-term healthcare facilities, schools, hospitals, residential areas, and prisons. We use the most recent census data to estimate the population that is potentially affected. The two most common modeling software used for offsite consequence analysis are RMP-Comp and Aloha. RMP-Comp is pre-programmed and is used as a plug-and-chug model that is very conservative. Aloha has additional parameters that are input and is less conservative. Now I will cover the regulations and threshold quantities. Anhydrous ammonia is regulated by CalArp, OSHA PSM, and US EPA RMP at 500, 10,000, and 10,000 pounds respectively. For aqueous ammonia, any percentage of aqueous ammonia is regulated by CalArp up to 500 pounds. After the 500-pound threshold is reached, whether it's 1 or 50% aqueous ammonia, you will be considered, you will be required to be compliant by CalArp. However, OSHA PSM and the US EPA RMP have specific thresholds above 20% that are regulated. So in the next row, you'll see for CalArp, it remains the same, that any percentage of aqueous ammonia is regulated above 500 pounds. For OSHA PSM, however, any aqueous ammonia above 44% exceeding the 15,000 pound limit will be regulated. And for US EPA RMP, with a solution greater than 20% and 20,000 pounds total, you'll fall under the RMP regulations. For chlorine, the CalArp threshold limit is 100 pounds, the OSHA PSM threshold limit is 1,500 pounds, and the US EPA RMP threshold limit is 2,500 pounds. Now I will cover a sample inventory calculation to show you which regulation that you are required to abide by depending on your threshold. For a 20% by weight aqueous ammonia solution at 2,000 gallons, we have the following. The density of a 20% aqueous ammonia solution is 7.73 pounds per gallon. For a 2,000 gallon tank, the total weight is 15,460 pounds of solution. Multiplying this by the 20% by weight, we have a total solution, or a total anhydrous ammonia quantity of 3,092 pounds. This is greater than the CalArp 500 pound limit, and thus you would fall under CalArp regulation requirements. For EPA RMP, given that the solution limit is 10,000 pounds, along with the OSHA PSM, you will not be required to follow their regulation. Now I will provide the first modeling example. The solution is an aqueous ammonia 20% weight solution. The hazard is toxic. The amount of solution is 2,000 gallons. We will be modeling this on Aloha for a water treatment plant. The container has a diked area of 100 square feet. Now to determine program level. Using Aloha, we insert the location of the facility and the building exchanges per hour. There's a predetermined input that you can enter for your building type, and it will give you the estimated exchange rate. For a single-story shelter, this is 0.26 exchanges per hour. For an aqueous ammonia solution, from the problem, we have that it's 20% by weight. The following physical properties are output from Aloha, with a boiling temperature of 117 degrees Fahrenheit, a partial pressure of 0.38 atm, an ambient saturation concentration of 37.9%, the hazardous component of the solution, which is ammonia, the CAS number, and the values of toxicity limits that we had covered in the earlier slides. Next, we input the atmospheric data. The atmospheric data from this site was 1.5 miles per hour from the west at 3-meter height. The ground roughness is Irvine, with a cloud cover at 5/10, an air temperature at 77 degrees, and Class F stability, and a relative humidity of 50%. For the source strength, we input the diked area of 100 square feet, the puddle volume of 2,000 gallons, which assumes the entire contents of the container are released, and a ground temperature of 77 degrees. Aloha limits the duration of solution release to 1 hour, assuming that the solution will not completely evaporate and that this will give you the furthest endpoint. The maximum release rate that was determined by the software is 1.25 pounds per minute for the 1 hour release time, and the total amount of ammonia released is 70 pounds. Given these parameters, the Aloha generated an estimated endpoint of 117 yards at 200 ppm. The following slide shows you a MAR-plot estimate, which gives you the population and housing units within the 111 yards. As you can see, this MAR-plot image shows that the toxic endpoint reaches other buildings and also reaches public roads. However, there is no population or housing units located within the area of concern. So, in conclusion, when determining the program level for this first modeling example, due to the fact that the toxic endpoint reaches offsite, the program threshold is above 500 pounds but under 10,000. The program is CALARP Program 2. Now I will cover the second modeling example. For anhydrous ammonia, we look at the given parameters. It's toxic, it's in a 2,000 pound cylinder. We'll be modeling with RMP comp. The site is a refrigeration facility. The vessel is located outside with no passive mitigation, and we want to determine the program level. The following slide shows the results from the information being input into RMP comp. A quantity released of 2,000 pounds with a release duration of 10 minutes gives a release rate of 200 pounds per minute. The reason that the release duration is 10 minutes in this example and not 60 like in the previous example is that this substance has a gaseous form, and it is assumed that after the entire release of the tank, the ammonia should be completely dispersed within 10 minutes. This would give the largest circle of concern. Since the vessel is outside, there is no mitigation measures, and the estimated distance to the toxic endpoint is calculated to be 0.6 miles. On the following slide, this is the Marplot circle of concern that shows a radius of 0.6 miles. As you can see, a much higher population is shown to be affected from this release. An estimated population of 2,684 people in 2,195 housing units is shown on the map. Now I'll cover program level. For a worst case scenario, if the sensitive receptor is reached, then you will automatically be bumped up to Program 2 facility. For the offsite consequence analysis, this means that you will have to do an alternative case scenario. This also may require some additional updates to your safety program. For Program 3, an alternative case scenario is also required. If you're in LEPC Region 1, a 0.5 mile radius should be included in your sensitive receptor map if an alternative case is less than 0.5 miles. For example, using the 0.6 mile worst case scenario and an LEPC 1 circle of concern of 0.5 miles and the alternative case estimated at 0.1 miles, it will give you a map that looks like this for each scenario. In conclusion, from our anhydrous ammonia worst case scenario, given that the anhydrous ammonia reaches offsite, the program level is CALARP Program 2. Modeling example number 3. The substance that we'll be focusing on is chlorine, which is a toxic substance with a quantity of 2,000 pounds. We'll be modeling this scenario with RMP comp. The facility is a water treatment facility, and the chlorine is stored outside. We want to determine the program level. Inputting the 2,000 pound quantity into RMP comp with a release duration of 10 minutes, we have a 200 pound per minute release. Wind speed is 1.5 meters per second, and the stability F class with 77 degrees. These are pre-populated in the program, and you're not able to change these parameters. The estimated distance to toxic endpoint is 1.3 miles. The following slide shows the estimated endpoint on Marplot with the calculation showing the population and housing units. The population estimated is 6,076, and the housing units estimated is 3,722. These estimates are always good to double check, especially if the population shows a 0, but on the map you're able to see a housing unit, as this data uses 2010 census data and may not be up to date for the current model. In conclusion, since The circle of concern reached sensitive receptors. It is regulated as a CalArc PSM Program 3. Please note that in this scenario, this facility is not EPA RMP regulated. That's because the quantity of chlorine on site is 2,000 pounds, which is above the CalArc and PSM regulated threshold, but below the EPA RMP regulated threshold. All facilities should know the properties of their chemicals associated with their process and the general hazards. Since ammonia is a popular chemical in refrigeration and water treatment, we will go over the properties of ammonia for you to keep in mind. Ammonia, which is NH3, is a chemical compound formed by 1 nitrogen and 3 hydrogen atoms. At standard temperature and pressure, STP, ammonia is a colorless gas that is lighter than air, has a distinctive pungent smell, and a high affinity for water. We'll also cover the properties of chlorine. Chlorine, on the periodic table noted as Cl, is most commonly known in its form of table salt, NaCl. However, in its gas form, it is highly toxic and is in the form of Cl2. At standard temperature and pressure, STP, chlorine is a green gas, heavier than air, and has a distinctive pungent smell. It is always important to know the properties of the chemicals on site so that you know the hazards that may take place and how to react to them appropriately. You can find the properties of any chemical that you have on site on a safety data sheet, which should be kept for reference from anyone dealing with these hazardous substances. Safety data sheets usually include the identification, hazards identification, composition, first aid, firefighting measures, handling and storage, physical and chemical properties, and stability and reactivity for any chemical that you may need. Another type of release that needs to be addressed on hazard assessment is solid releases. Solid releases are not currently supported in modeling software as they're very difficult to model since they do not behave as a gas or a liquid. They have extreme physical properties. They have extremely low vapor pressure and very high boiling point. So they usually have a very low toxic endpoint. If you have any questions, please message the producer in charge of this webcast, or you can email me at justin.koehler@rmpcorp.com. Also, you can contact me on LinkedIn at the following link. Thank you very much for your time, and have a great day.